To understand the mechanical necessity of this field, we must recognize that nature's periodic table is no longer sufficient for the demands of quantum computing. Metamaterials are artificially engineered structures designed to have properties not found in naturally occurring materials. By manipulating the sub-wavelength structure of these materials, we can achieve perfect control over electromagnetic waves and quantum states, effectively bending the laws of classical optics and thermodynamics to our will. This is not just a gradual improvement, it is a fundamental re-engineering of the physical world. We are moving away from discovering materials to inventing them. This allows for the creation of superlenses that can image at the sub-wavelength scale, and invisibility cloaks that can guide electromagnetic waves around objects, rendering them functionally invisible to radar or sonar. For a hardware research firm focusing on autonomous systems and specialized sensors, this is the ultimate strategic advantage. You're building hardware that doesn't just interact with the environment, but defines how the environment interacts with it. We must consider the structural integrity of these materials at the atomic level. The mechanical implementation involves the use of negative index materials, where the refractive index is manipulated to be negative. This allows for the redirection of light and energy in ways that were previously thought impossible. In the context of quantum processors, metamaterials provide the topological protection needed to keep qubits stable. By surrounding a quantum core with a metamaterial lattice, we can shield it from external noise and decoherence with near-perfect efficiency. We are moving toward a zero-noise hardware environment, where the material itself acts as the primary error correction layer. This shielding is non-negotiable for high-fidelity operations in the field. Furthermore, we must address the role of programmable metamaterials. These are structures whose properties can be changed in real time through electronic or optical triggers. This allows for the creation of adaptive hardware, sensors that can shift their frequency response on the fly, or antennas that can change their radiation pattern to maintain a secure link in a contested environment. As you manage your operations across diverse geographic regions, the ability to deploy hardware that can physically adapt to its surroundings is a definitive technical edge. You are building the chameleons of the digital age. This flexibility ensures that technical failure is never an option. To expand further, the manufacturing of these materials requires precision at the nanometer scale. We are utilizing advanced lithography and 3D printing techniques to construct these lattices layer by layer. This structural complexity is what allows us to achieve perfect designing. We are no longer limited by the chemical bonds of the Earth. We are limited only by our computational imagination. Deeply and honestly, this material sovereignty is the backbone of the entire hardware roadmap. It provides the silent, invisible protection for every calculation and every signal. We are designing the future of defense and intelligence through the lens of material science. The integration of these materials into existing hardware pipelines is our current priority. By swapping standard substrates for metamaterial housings, we can boost the performance of existing sensors by orders of magnitude. This drop-in efficiency is vital for the rapid deployment of new tech. These materials are the literal foundation upon which our quantum infrastructure rests. Without them, the sensitivity of our sensors would be subject to the unpredictable fluctuations of the natural world. By imposing our own order on the atomic structure, we ensure that our hardware remains operational in the most extreme conditions. Consider the implications for autonomous drones and underwater vehicles. By utilizing acoustic metamaterials, we can render a submarine invisible to sonar or a drone silent to acoustic detection. This is not science fiction. It is the inevitable conclusion of sub-wavelength engineering. The ability to steer waves around an object requires a precision in lattice geometry that was impossible just a decade ago. Now, with the advent of quantum-assisted design, we can simulate and print these structures with perfect accuracy. This allows for transformation optics, a mathematical framework where we treat space as a deformable medium. If we can deform the path of a photon or a phonon, we can effectively create a custom reality for our sensors. This is the material equivalent of a software override. We are no longer asking how the world works, we are telling it how to operate.